Okay, so we are continuing our discussions. So in the last hour, we have found the following. If I have a bandpass process, let me see. Well, I have lost my process. If I have a bandpass process, so this is bandpass, but wide sense stationary, random process, n of t. Now this will be its low pass equivalent process, okay, and we have seen that this is also wide sense stationary, and it has real and imaginary parts in the low pass equivalent, okay. So we have also found the power spectral density of this low pass equivalent process, something like this. I mean, this is just an example how we generate this. So that is the end. So our next topic is, now I would like to understand, the real part and the imaginary part of this low pass equivalent process. So how can I work that? So my goal is doing something, let's keep this, similar to this one, but for Ni and Nq. So how can I do that? So the next question is, we have left this point, finding power spectral density of the real part of low pass equivalent, Ni process, and the imaginary part, Nq, quadrature component of this low pass equivalent. So how can I do this? So let me let me write Ni of t, which is simply the real part of this. The real part of this is this, okay? And the low pass equivalent is, this is the analytic process, this one. It is shifted to the lower frequencies by this, okay? So again, this is a random process because this is a random process. Now I'm looking for a mapping between this random process and this random process. If you want, fix a time in your mind. If I have a fixed time, let's t is equal to 5, so I have a number over here, number over there, but that number is, related with this random variable at this point. So this becomes a functional mapping of a random variable. It will be something like that. So this is nothing but step 2 of the earlier operation, okay? Shifting, step 2 of the earlier operation. So can I write the following then? So this is also equal to n of t. Sorry. Let me write, okay, let's do not write anything else, because that's good enough. So what was n plus of analytic signal? So this is n of t plus j n hat of t. Am I right? N of t plus n hat of t. Okay, now ni of t. So if I know n of t's, let's say autocorrelation, etc. and etc., n hat of t is autocorrelation and cross correlation with cross correlation with this one, let's say, maybe I'll be able to calculate this ni. Okay. So, but before that, let me do this multiplication. This blue box is multiplied by, let me put another box, the other blue box, and then I'm taking the real part. So what do I get? I multiply the real parts. Okay. And then the imaginary part is multiplied by the imaginary part. But this imaginary part has minus sign over here. Am I correct? Okay. If I do that multiplication, because this is cosine minus j sine. Okay. So the real part is real cosine times this minus j times this. Okay. So I get this. That is the end. So how about nq? Okay. Now this part is multiplied by cosine. And this is multiplied by, this time, minus sine. This is, this is multiplied by 2 pi fct. Is this correct? And I have a plus sign over here. Let me see. This is, plus. Let's do it one more time. This is equal to cosine 2 pi fct minus j sine 2 pi fct. This times that, minus j times j is 1, so I get this. Okay. So how about this? This times that, this times that with minus sign. Okay. Now it is correct. So what do I need to do? So I need to find the statistics of this. Ni and Nq. So how can I find statistics of Ni and Nq? So the goal is finding, let's say, the statistics, meaning that, for example, autocorrelation. If it is Weissan stationary, I'm not sure, but it should be Weissan stationary for the sake of this discussion. R Ni T, R Nq tau, R Ni Nq of tau from the relation, let's say, double star. From the relation double star, let's say. Okay. So how can I do this? Well, I will do the following. First of all, I will write this. You are not completely responsible from this part because, I mean, it's something easy, but maybe it's not required for the sake of this course. So how can I write this one? So Ni is equal to cosine 2 pi fct, I need more space, sine 2 pi fct. This is a matrix. Then this is minus sine 2 pi fct cosine 2 pi fct times n of t and this. Do you agree? And het of t. Is this correct? The mapping. So since this is nothing but a linear combination of n of t, and het of t is Hilbert transform. So I should be able to write it as a vector matrix multiplication because just linear combination of them. But this matrix is rather special. Well, I will call this matrix, I don't want to write it again and again. It's a matrix changing by time, R of t. Okay, I have something like that. And what is the determinant of this matrix? Cosine square plus sine square. Determinant is 1. Okay. So essentially this is like a rotation matrix. So that rotation angle is, if you consider this like theta is the angle of this argument, that is changing by time. And I have something like that. So what's my goal? So how about this? If I calculate expected value of this one. Sorry. So I'm trying to, let's say, catch, or how to say, I'm trying to hit, I don't want to say kill, multiple birds with a single stone, okay? So if I do this calculation, if you wish, we can put the conjugates also over here, but everything is real valued because, you know, ni is already the real part of the everything is real valued, but if you wish, we can put the conjugates to show that this is the autocorrelation calculation, but we don't need the conjugates. ni, nq, these are real valued processes, clearly. But if I do this, what do I get? This times that. Hopefully it will be y-sans stationary and I don't be observing a t over here. I'm not sure, maybe it will be depending on t, but this would be, if it's y-sans stationary, Rn of tau. Later on we will evaluate this. How about this? This times that after expectation. So this is the reason that I'm trying to catch, let's say, nq, ni, this times that. So I'm trying to catch 4 birds, all of them. So, okay, with this calculation. Do you see what I mean? So if I can do this expectation, then I will be getting a matrix. 1 entry of this matrix will be autocorrelation for the in-phase component in the process. 2 component of that matrix will be autocorrelation for the quadrature. 1-2 component will be cross correlations and so on, which is good. But how am I going to evaluate this? Now, let's go over here. Now, this is equal to this R matrix, expected value of, let's do not write this, R matrix times, well, this is n of t. Now this part is this. Now I should be writing this one. So how am I going to write that? So this is transpose of this, but r t minus tau, as you see, the same vector. So as you see, linear algebra is your good friend in such calculations, because with transpose and so on, you can do these operations very orderly. Well, let me write. It's quite obvious, but transpose. Do you agree? So this would be this row vector. Only difference is that, so this was for t, so I replace all t's by t minus tau. I'm not dealing with conjugation anymore. Okay? So I have that. So how about this? Now, again, linearity. There are a bunch of additions and multiplications over there. So these coefficients in RT, or the entries of this matrix, they are not random. So I can write this as, pull this out. Okay? Okay, let me do it one more step before that. Now this is equal to that, this part. R of t is a matrix and t minus tau and transpose of this matrix, transpose of this vector times. Do you agree? This part is equal to this. Well, because this argument is, I have R matrix times a vector, vector 1, times another R matrix. Let me write R1, V1, R2, V2, but there is a transpose over here. R1, V1, R2, V2, okay? So this part is V2 transpose R2. So then this part remains as before. So I have this. So because of this transpose, I have two vectors, which we call outer product of these vectors. So does this make sense? This is a 2 by 2 matrix. This part is a 2 by 2 matrix. After this bracket is 2 by 2. This is 2 by 2, while the end result should be 2 by 2, and so on. Okay, so I should be, okay, then let's write this, taking the expected value of this. Okay. but this R is non-random, meaning that it's deterministic. Okay? Non-random means another word for deterministic. So I have R of t matrix times expected value of this, R of t minus tau. Actually, we are approaching our result, but we should be a little bit patient. This times that expected value, Rn of tau. This times that, Rn n hat of tau. Oh, this is t minus tau. Because this one. Okay. This times that. This times this, Rn hat n of tau. This times that of that. So exactly the same thing that we have done. I have a vector and transpose of the vector. I take the expected value. First I calculate this matrix and take the expected value of every entry of it. Okay. So this times that is the 1, 1 entry of this matrix. After expectation I get this. This times that is 1, 2 entry of this matrix. I get that. Okay. Very good. We are almost there. So at the end of this calculation, I'll be getting a 2 by 2 matrix, and then I will say that Ni will be, 1 by, at the end of this calculation, the corner component of the product will be Rni of tau. Okay. But do I know this, that, these kinds of things? So of course I know the, Rn of tau, because I know this is my bandpass process Rn. Okay. But how about these ones, cross correlations, its Hilbert transform, etc. So at this point we make use of this basic facts. So what do I mean by basic facts? Now n and n hat, how they are related? Well, 1 over pi t n hat of t, am I right? So for example, I need the autocorrelation of the output, R and hat. So how can I, find that? Well, let me use this from basic facts. Let me try to use this. Output power spectral density is nothing but input power spectral density, am I right? Times magnitude spectrum square. So if this is, one more time, let me write h of t. So minus j signum f, okay? So this is h of f magnitude square. Do you agree? Because this is our filter. So just for visual purposes, let me sketch this. H of f, sorry, not j, h of f divided by minus j. I mean, I need to draw this. So essentially, this is like signum f. Okay. 1 minus 1. So if you take the square of this, it's always 1. The magnitude of minus j is 1. So this is always 1, as you see. Okay. Of course, I'm not worried about what will happen at 0. Okay. So 0 is another issue. But I'm not worried about that. So I see that this is equal to Sn of f. Very good. Because their autocorrelation should be the same then. Okay? Because this is what we call like an all-pass filter. Okay? It's passing all frequencies. Its magnitude response is 1. Okay? All-pass kind of a filter. So I have this. How about this? I need something like this. N hat. Not n star, but oh, this is, I made a mistake. Output is n hat. So this is supposed to be n hat. This is output process. So this is input x, output y as a function of frequency. Input times h of f, but with conjugates. Do you agree? Something like this. So this part is, I have written this. Okay, so let me write this one because I also need that one. N hat n. So this is h of f. Okay. Times this input. Do you agree? Okay. That is the end actually. So from here, can I write, if I take the conjugate of this, this becomes plus. This is, there is no conjugate minus. So they are negatives of each other. So this is Sn m prime. I have this. Okay. Because if you take the conjugate, this becomes plus j. This is always minus j. So they are negatives of each other. Well, very good. But what do I need? I don't need power spectral densities, but I need autocorrelations, as you see. How much time do we have? We have plenty of time. Okay, so if I take inverse Fourier transform, so what do I have? So this will be r n hat of tau after this operation will be equal to r n of tau. Because their power spectral densities are equal, their autocorrelation should be equal. Okay. So how about this? R cross correlation. R n hat of tau, if I take the inverse Fourier transform of this, is equal to, well, maybe I should check this one first. R, this is easier. N hat first, n of tau, is equal to, how about this? How about this one? Would you agree? A little interesting. Now this is the Hilbert transform of Rn of tau. So how do you take the Hilbert transform of a function? You take the Fourier transform of this function, which is this, and multiply by this. Do you see what I mean? It's very simple. So this becomes its inverse Fourier transform. This is like the, this is like the convolution theorem essentially. Okay. So this is that one, Hilbert transform. Okay. So Hilbert transform of a function is in Fourier domain because it's like a convolution operation. This thing, its frequency response of 1 over pi t is this. So if you multiply, you get this. So interesting thing is that now I know this. I know this one. This is my bandpass process autocorrelation. Okay. So this is, let me write one more time. Hilbert transform of Rn of tau. This is the Hilbert transform of that. Again, I know this one, so I can calculate this. So how about this one is then? This is negative of that. Well, because they are negatives of each other. So this is this thing minus, I have this. Okay. So what should I do next? So first of all, is this thing correct? Let's see. Rn hat, Rn of tau, n hat and Hilbert transform of this, and n hat negative of that. Okay, we are almost there. So what do I mean we are almost there? Now, I have calculated this. Previously, I have no idea about this term, for example. Well, of course, I know my bandpass process. I know bandpass process, power, spectral density, its autocorrelation. This is my very first input. But I didn't know this. But this turns out to be Rn of tau. Okay, very good. How about this one? This one is this thing. This is the Hilbert transform of that, but with a minus sign. This is Hilbert transform of this autocorrelation of bandpass random process. This is the Hilbert transform of the autocorrelation of this bandpass process. Okay, R n of tau and n hat. I have over here, and this is this. Rn of tau, no changes for that. We are done. This is the end actually. So what should we do? Now, final step. I would like to write this over here. Now, I will write this R matrix, cosine 2 pi f ct, sine 2 pi f ct, minus sine 2 pi f ct, cosine 2 pi f ct, times this matrix, R n of tau, R n of tau, minus R n Hilbert transform of tau, R n Hilbert transform of tau. And I have t minus tau over here, but I should be careful. There should be a transpose over here. Okay. Once I take this, there should be a transpose. So if I have a transpose, this minus sign goes over here. But it's difficult to write. T minus tau. T minus tau. This is sine T minus tau. T minus tau. Is this correct? Let me see. Cosine minus sine. I have this. So that is the end actually. So matrix number 1, R of t, times matrix number 2, I know this matrix because I know Rn, and matrix number 3, R t minus tau with transpose. Okay? So if I do this multiplication, I won't be doing it the multiplication, but I'll be just writing the result. So final step. We go this way. Let me try to find this. Let me use small letters, Rn of tau, cosine 2 pi fc tau plus Rn hat of tau Rn of tau sine 2 pi fc tau. And we have Rn of tau 2 pi fc tau this okay. So if you multiply these three matrices, so what's happening? Actually, it's a little bit interesting. At the end, we get this 2 by 2 matrix, but there is no T in this 2 by 2 matrix. Very interesting. So this would be then, if my multiplication is correct, this would be equal to remember, at the beginning we have started that this would be R. In phase component autocorrelation, it should be something like that. Okay? So this would be R Ni NQ of tau. Okay? And then this would be R NQ of tau according to this. And this would be R NQ Ni of tau. Do you agree? Now I have those statements. So for example, let's check one of them. So how can you calculate the 1, 1 entry of this matrix? This is the 1, 1 entry. So you should multiply this matrix. You should focus on first row, first column entry of this multiplication. Okay? That is it. For example, Rn of tau. This is multiplied by this term and this term. Do you agree? If you do this multiplication. This is 1, 1 entry. 1, 1 entry, forget about this vector. It should be first row times first column of this, isn't it, right-hand side? So the first column will be related with this one. So this A matrix times B. So I'm interested in this inner product, this matrix times this. So about the coefficient of Rn of tau? Of course, this requires more exercise in maybe linear algebra, but coefficient of Rn of tau is this times that. How about this coefficient of Rn of tau? This times that. So pull Rn of tau in common brackets. You have cos this, cos that, plus sine this, sine that. This is cos this minus that. Do you see what I mean? Cos expansion. There is a cos. If you do this product, you will see. So this cos expansion, this minus that part, gives you this is this, that is that. This minus that is 2 pi fc tau. Okay? That is how you get that cancellation. So as I have said, you are not fully responsible for this, but that is our result. So in the next lecture, we will be using these relations, but these relations are difficult to remember in autocorrelation domain, let's say. We will be using these relations in the power spectral density. Okay? In the Fourier domain, it will be easier to remember how you derive these expressions. It will be much easier to remember. It will be something like a graphical picture like this. So I will be taking essentially the Fourier transform of this. It will be a simple operation such as this one for the power spectral density of Ni process. We'll be calculating that. Okay, so as I have said, you are not fully responsible for this because this is a little bit, even though it's simple, but it requires more exercise in linear algebra perhaps, in terms of vector thinking and so on. You are not fully responsible for this one, but just pay attention if you are interested. And you can see that everything goes very right again, isn't it? These cosine expansions, you know, these kinds of things, everything goes very right, and I'm getting a Weissen's stationary process. Because do you remember at the very beginning we have said that I'm writing this, and I'm hoping that Ni, Nq will be only function of tau, but not t. So you see that that cancellation also occurs over here. T is cancelled at the very end because of my, a little funny comment. This minus that is free of t. That is the issue. You can do the other calculations and verify this is correct. But let me see, just to make sure that I'm not making any mistakes, just to maybe clarify this. Let me write this point, and then in the next hour we will continue from that point. Autocorrelation of Ni of tau. Sometimes I use capital, sometimes I use small letters. It's not important in this course at least. So this is number one. Number two is cross correlation. This is sine 2 pi fc tau minus cosine 2 pi fc tau. So this is our final response. Okay. Let me just check this. This is this. This should be equal to this. This is NI/NQ sine this, and negative of this is this. Minus sine plus sine. Okay. Okay, so that's all for today. So we will continue in our very last hour with the Fourier transform of 1 and 2. Okay.